Looking a little bit more into now drag. Kind of talked a little bit about it with that angle of attack. We got to think about, why do I get drag when I'm producing lift? So just a quick review, our two types of drag. We're looking at parasite drag, which is a result from the form of the aircraft, form drag, the shape of the aircraft, interference drag, and just the fact that air is going over the skin of the aircraft, so skin friction drag. And obviously, the faster you go, the more velocity, the more drag you get from parasite drag. When we slow down the aircraft, we get a reduction in parasite drag, but because we're counting on more lift from angle of attack, we start to get more induced drag to a point where then we reach the stall point. So we need to remember that when we combine both of these together, we can come up with this total drag curve. And the low point there, point A on the drag curve, is a very special point. A couple things happen there. And the FAA wants you to know these points for knowledge test. First thing is, well, it's called the maximum lift to drag ratio. So you do need to understand that. That is the point where you get the most lift and the least amount of drag. So the ratio of lift to drag is the greatest at that point. That does yield the best glide of the aircraft. So that would give the aircraft the smallest rate of descent in an engine out situation. That would give it the most time in the air. And hopefully, if you fly it correctly, it gives you the greatest distance to get to a place to touch down with an engine failure. It's also the point where we get the best range of the aircraft. Wherever we can, whenever we have the minimal drag on the aircraft, then we can actually get the aircraft to go farther with it. Looking at drag, there's some concepts here that you should know about, especially for the knowledge test. If you take the airspeed and double it, say if we go from 60 knots to 120 knots, the effect on drag is that it will quadruple. So doubling airspeed quadruples drag. In order to go faster, you must octuple the power. So it's a factor of 8. Increase your power by a factor of 8 just to go faster. So this is why we run out of engine power in level cruise flight and can't go any faster. Right? That engine's only so big, so we can only go so fast with it. Of course, that's something our air race team is going to find out. They begin their training soon. When our air race team goes, they just go full throttle. They fly as fast as they can. So learning some aerodynamic principles helps make that aircraft go even faster. All right, so that's a little bit on the drag. Let's talk a little bit more about induced drag. This concept of when I am slowing down and producing lift, I'm also producing a little bit of drag with it. When I take a peek on the left side here, I have a relative wind. It's relative to the direction of the flight path, not necessarily the nose, but to the flight path. And we know that lift is developed at a right angle here to that relative wind. Lift is produced at a right angle to it. Well, something interesting happens, right, three-dimensionally with the aircraft. When that wind hits the leading edge of the wing, some of it goes down beneath it, but some of it kind of changes direction and goes up above. right? And that creates a little bit of an upwash effect. In that upwash ahead of the wing, takes this relative wind and tilts it. So now the relative wind is tilted upwards. Lift acts perpendicular to the relative wind. So this new vector here is really where lift is acting, which means lift is now acting not only upward, but a little bit behind. That means it's pulling you back a little bit. So that's what we call induced drag. So the difference between where the lift should be and where the lift is tilted back to, that's your induced drag vector. Now this induced drag vector does get affected when you get close to the ground. In fact, that three-dimensional airflow gets disrupted the lower you get to the ground. When we're talking about ground effect actually begins at one wingspan above the ground. Very insignificant at that point there. And it's not until you get to a half wingspan that you begin to notice the effect of the ground. Hence, ground effect. So the FAA is going to ask you some questions on whether you are entering ground effect or exiting ground effect. And the perspective you have to think about is, if I maintain the same angle of attack. Okay. So if I maintain the same angle of attack as I fly into ground effect is removing that tilting of the relative wind, which means it's reducing the amount of induced drag. So effectively, as you enter ground effect, lift is not acting as much behind you as it's starting to act more upward. Hence, you have more lift. That's why if you aren't flying at the appropriate speeds or don't bring the power to idle, you're trying to land, you're just going to float down the runway because you don't have that extra drag to slow you down. If you are leaving ground effect with the same angle of attack, as you leave, you get past that one wingspan, okay, that relative wind vector is now being tilted. Lift is being tilted rearward. You're increasing lift. I'm sorry, said that wrong. You're increasing induced drag. So the overall effectiveness of the lift is less, so lift would decrease on that. And that does mean that if you somehow got airborne at too slow of an airspeed, it is entirely possible for that aircraft to stall once it leaves ground effect. All right, so there's just a little bit of a graphic to help you understand. Outside of ground effect, we have a tilting of the lift vector as the relative wind got tilted up. That's all eliminated the closer we get to the ground. All right, so how you doing so far? You need a break. I'm not hearing a yes or a no. I'm seeing a head shake, Grace. Be a captain and speak up. Do you all need a break? All right, I'm hearing a no. All right. The captain has spoken.